Now let's talk about what we call the effective or the RMS values of voltage and current. And the concept of the RMS value actually kind of goes back to the days when there were competing systems for how we were going to power the country. Edison Electric was doing DC power, DC electricity to people's homes, and Westinghouse and GE, with Tesla, for example, doing a lot of the theoretical work behind that, wanted to do AC power. So we had two competing systems, and just as a comparison, let's say we were given two circuits. And one of those circuits is a DC circuit. So let's say in this case, it's a DC current flowing through some resistor. And then we have a second source. And this is a periodic AC source. And this one is connected to an identical value of resistor. So imagine back in the days of, back in the late 19th century, when you had two competing companies coming to you and saying, buy our power, buy our power service, DC is good, no, AC is better. You have people arguing about this. Well, what do you care about as a consumer? You care about how hot that resistor gets. In other words, you care about the power that gets delivered to you. The problem was DC and AC signals cannot be easily compared, as we've already seen. So people needed a way of directly comparing AC and DC with a single number. And that idea of taking a single number to compare those terms is what led to what we call the effective or RMS values. So here's the question we want to answer. Given the same RL in both circuits, what value of IDC results in the same average power dissipated in the load as the periodic current source? So we want both these sources to generate the same average power dissipation in both load resistors. What's the yardstick? How do we compare them together? Well, this is what we're going to do. We want P average DC to be equal to P average AC. And in this case, the periodic waveform, the AC waveform. We want those two average powers to be the same, generated by those two sources. Okay, let's write the equations. What is the average power in the resistor due to the DC source? Well, we learned that very early in this course. That is IDC squared times RL. That's the P average DC. What about for the periodic signal? Well, in this case, this is going to be equal to 1 over T integral from 0 to T I periodic squared times RL dt. So all we're doing here is we're taking the periodic waveform, we're just integrating from 0 to T, so we're assuming T0 is just 0 to make it easy. And then we're just applying the definition of the mean, the average value of the I squared R function. Okay? So we're taking the same I squared r and we're just looking at the average value. Okay? So I'm now comparing the two. Let's do a little bit of math. So in this case, I can factor the RL out from both sides. So I can actually cancel those out. And in this case, I can then take the square root of both sides. And if I do that, what I get is the following. That IDC is equal to the square root of 1 over t from integral from 0 to t, I periodic t squared dt. If I meet this definition for IDC, I will have the same power dissipated in both resistors. Well, from this, I can now define a new term. I'm going to define what we call the effective or RMS value. RMS, what does RMS stand for? Root mean squared. And in fact, look what we just did here. IDC is equal to the square root of the mean of the squared function, RMS. Okay? I'm going to define IRMS or I effective as simply that function. So the root mean squared or effective value are the same thing, just different terms for the same thing. And they're going to be equal to the square root of 1 over t from 0 to t times I periodic t squared dt. That's the RMS value of the current. All right? What we're saying is the RMS value of a function is equivalent to the DC value if I were connecting a DC source across that same load. Let's see how that works. First of all, how do we calculate the RMS value of a sinusoid? Because obviously that is the kind of periodic function we care about, is a sinusoid. And we're going to do it this way. Let's assume our current. Let's let IT be equal to Im times cosine omega t plus theta. And therefore, IRMS or I effective will therefore be equal to the square root of, well, in this case, t is equal to 2 pi over omega, so 1 over t is equal to omega over 2 pi, and so therefore I'm going to write this as omega over 2 pi, integrate from 0 to 2 pi over omega times Im squared times cosine squared omega t plus theta dt. So I've simply written this, substituted for the value of the period for a sinusoidal function. And now I'm going to use a trig identity that lets me take a cosine squared value and decompose that. And this will be equal to the square root of omega over 2 pi, integral from 0 to 2 pi over omega, times 1/2 Im squared, times 1 plus cosine 2 omega t plus 2 theta dt. So cosine squared x is equal to 1/2 times 1 plus cosine 2x. Now I can take this and break this into two parts. This will be equal to the square root of omega over 2 pi, integral of, let's see, let me do this, omega over 2 pi times the integral of 0 to 2 pi over omega times 1/2 Im squared dt. So I'm just breaking this up into two integrals, plus 0 to 2 pi over omega times Im squared times cosine 2 omega t plus 2 theta dt. So I've decomposed this into two integrals, this plus this. And what do you know? Once again, I'm integrating over a period for cosine 2 omega t. And what did we see before when we did that? The area under the curve must be equal to 0. Therefore, this integral is equal to 0, that portion of the integral. So all we really have left is this piece. So this will be equal to, in this case, this is just a constant times dt, so this will be equal to omega over 2 pi times 1/2 Im squared. We factor that out, and we evaluate this as t evaluated from 0 to 2 pi over omega, which is just equal to the square root of omega over 2 pi times 1/2 Im squared times 2 pi over omega. And very nicely, the omega terms cancel out. And therefore, what we get is that RMS is therefore equal to square root of 1/2 Im squared is just equal to Im over the square root of 2. So I take that, take the square root, and I get this. This is the RMS value of a sinusoidal current. In other words, what we're saying is this. A sinusoid of magnitude Im will, in effect, cause the load resistor to have the same average power as a DC source of this value. So a sinusoid of magnitude Im will provide the same average power to a load as a DC source of Im over the square root of 2. So now we have a way of comparing sinusoidal AC to DC by using the RMS value. So what else does this do for us, this RMS concept? Well, we also get this. If IRMS is equal to this, then IRMS is equal to I effective is equal to IM over the square root of 2. We can also very easily, using the same type of math, prove that the effective voltage value works the same way. Effective value of voltage, or RMS value of voltage, is the same thing as V sub m over the square root of 2. So here are RMS values. We also recall that this must be true. We recall that P is equal to Vm squared over 2R. Vm over the square root of 2, Vm squared over 2. In other words, this must be equal to Vrms squared over R. And P is equal to Im squared over 2 times R, which means that'll be equal to IRMS squared times R. It's very nice. That 1/2 term disappears. Now our AC and our DC power equations look the same as long as we're using RMS values. So this is true for a resistor. Which, of course, that's the only place where we're going to have non-zero average powers in a resistor. But we also note for any element. P is equal to Vm over 2 times cosine theta sub V minus theta sub I. This is the average power for any element. We showed this equation before. I can do the same substitution. I can take this, decompose it into the square root of 2 times the square root of 2, and I can rewrite this and say this is equal to Vrms times IRMS times cosine theta sub V minus theta sub I. So this is also true. In this equation, we also get rid of the 1/2 term if we use RMS values. Now, as it turns out, when we're talking about electricity that comes out of the wall, what does the power company use? They use RMS values. They want you to be able to compare what comes out of the wall with a DC value. So, for example, for an electrical appliance, if you look at a label on an electrical appliance and you see how it's rated, you'll see something like this. You'll see, for example, 120 volts at 1 amp. And of course, this is assuming here in North America we have 60 cycle or 60 hertz power. What does that mean? What this means is it's really 120 volts RMS at 1 amp RMS. So when you look on an appliance and see these ratings, they're actually telling you that these are RMS values. They behave like DC values, so the power is going to be 120 watts when you calculate it. In fact, if you think about it, what actually comes out of the wall? You probably have heard that we have 120 volts. That's the voltage that comes out of the wall. It is 120 volts RMS. It behaves as if it has it's like a 120 volt DC source as far as how it heats up a resistor. But what do we really see? If you actually look at what comes out of the wall, what you'll really see is you'll see a sinusoid with a peak value of 120 times the square root of 2 to give us 120 volts RMS. So what you really see is you will see a sinusoid with a maximum and minimum value of about 169.7 volts. So what comes out of the wall is a sinusoid with a magnitude of about 170 volts, plus and minus 170 volts. But as far as how this sinusoid will heat up a resistor if you connect it to it, it heats it up exactly the same as if you took a 120 volt DC battery and hooked it across that source. So effectively, this sinusoid acts like 120 volts DC. And that's what we mean by effective values. But by using these effective values, we very nicely get rid of these 1/2 terms, these 1/2 multiplier terms. And as that turns out, we're going to see that makes some of our other power calculations a lot easier too, because now the DC and the AC power calculations look the same. Okay, now up to this point we have only considered the average or real power. Although, as we mentioned before, obviously something's going on with capacitors and inductors. They don't dissipate power, but clearly they are absorbing and releasing energy back into the circuit. How do we characterize that? And for that matter, how do we deal with, the fact that we're going to have both a real and an imaginary component to impedances when we're calculating the effective power? Really, when you look at this, we're not really doing this logically. We were doing all of this when you think about it with phasors. So we were calculating voltage and current phasors with phasor analysis, and then we kind of got away from that. We basically went to a situation where we started looking at the magnitudes and pulling pieces out of the phasors. But can we actually calculate power using a pure phasor calculation? Well, let's look at that next time. And that basically, let's look at the concept of complex power that puts all of this together and gives us a way of solving for the AC power for any circuit, any element.